Interference. This is a review from last unit. Two waves are in phase when they differ by an integral number of wavelengths, such as 1 lambda, 2 lambda, 3 lambda. And that's this column right here. And that's where you have constructive interference. When you add these two waves together, superposition, you get a bigger wave. They are out of phase when they differ by an odd integral number of half a wavelength. And that looks a lot better when you show the equation as opposed to words. So when they're different by lambda over 2, 3 lambda over 2, 5 lambda over 2, etc., then they are out of phase. If neither condition is met, then they are partially out of phase. So when they're completely out of phase, we've got the trough meeting a maximum here, maximum positive. They cancel out, right? It'd be like a -5 here and a +5. So they get to be 0. So that's destructive interference. And you have partially out of phase when it's neither one of them and you have a weaker signal there, but not 0. Let's apply that concept to sound waves. We have two sound sources, green and red. They emit sound with the same amplitude and wavelength and are switched on at the same time. For this first example, both waves travel the same path length, that's a fancy word for distance, to a listener. The waves add together in constructive interference. The sound waves are in phase and their sum will be a maximum, and the listener hears the loudest possible sound, because at any point you can see how these two add together and make a bigger amplitude. Now move the red source so its waves travel a path length that is 1/2 lambda different from the green source. They will add together in destructive interference. The sound waves are completely out of phase and their sum will be 0. The listener will not hear anything. See where you've got the peak here meeting the trough here. They add together to form 0 because your path difference is now 1/2 lambda. This wave started here. This wave started a distance of 1/2 a lambda after it. Now move the red source closer to the listener so the sound waves travel a path length difference that is an odd multiple of 1/2 lambda. We're going to use 3/2 lambda as an example. Once again, they are adding together in destructive interference. The peak of this one matches the trough here. They add to 0. The sound waves are once again completely out of phase and their sum will be 0. The listener will not hear anything. Finally, move the red source so the sound wave travel a path length difference that is an integer multiple of lambda. We're going to show 2 lambda as an example. See the distance here? It's 2 lambda closer to the listener. Here we have the peaks matching each other again. So that's going to be constructive interference. The sound waves are completely in phase and the listener will hear a maximum sound. So completely in phase, constructive interference, maximum sound. Let's look at this same phenomenon in a little different way. Sound waves interfere in the same way that other waves do in space, like water waves. Constructive interference occurs when two crests, or peaks, or two troughs meet. When a listener is located where constructive interference is occurring, there will be a loud spot. So our example over here, the blue waves are emanating from this speaker, and kind of the purple ones are coming from this one. And they interfere where they touch. These points here, where they're interfering, we're calling that constructive interference, and you will get maximum sound there. Destructive interference occurs when a crest and a trough meet. When a listener is located where destructive interference is occurring, there will be little or no sound. This time, their destructive interference is occurring at the green dots. So you can see, hopefully, here's the blue wave here. Let's say that's the maximum. Then it goes down to a minimum at this point here, just as the purple waves reaching a maximum. So they're going to cancel out. And that pattern fits going in that direction. So if you're over here, you will hear nothing. That will be destructive interference. Now let's place a microphone at several places and the sounds are fed into an oscilloscope. And there's our picture of what the oscilloscope is showing us. And that shows the sound amplitudes. Destructive interference occurs along the radial bands indicated. So hopefully you can see it's white over there. that means there's no sound. So that's where your destructive interference is occurring. Constructive interference occurs where the scope shows alternating light and dark bands, maxima and minima. So right there, you're going to have your constructive interference of your waves. Here, it's all white, you see nothing. Here you go maximum, then it goes to 0, then it goes to a negative maximum. So that wave is going to look like this. All right, and that's where you have constructive interference. Along here, your wave is doing this. They're canceling out. Now we're going to get an equation for this. We have two speakers separated by a distance d and a distance L from a microphone. We're going to have the microphone moving up and down on that post there. Can you see that light gray arrow? That's going to record the loudness of the sound from the speakers. The microphone, and we're going to show the data, well, we're going to put the words there, it records a pattern of alternating loud spots and places with no sound. The sound from each speaker, except for point A on the center line, travels a different path length before reaching the microphone, so you get that constructive and destructive interference. Along this line, hopefully you can see the sound, both of them will have the same path length, so that will be constructive interference. So you have a loud spot right in the middle. And then, let's just show, at this point here, the sound, right here it's going to come that distance, here it's going to go a longer distance. So you're going to get different types of interference depending on the path length differences. It'll either be constructive or destructive. So if the difference in path lengths traveled, right, there from that one and this from the other, is an integer multiple of the wavelength, you have a loud sound. That's constructive interference. If it is an odd integer multiple of half a wavelength, it results in no sound, destructive interference. Using some math that is beyond the scope of this course, and that'll be for your AP Physics courses, the locations of the maxima, once again constructive interference, and minima, destructive interference, are found to be these two equations here. Here's your maxima, x is equal to m lambda L over d, and the minima, almost the same, but instead of m, you have m plus 1/2. M is the order of the interference fringe. M can be 0, plus or minus 1, plus or minus 2, etc. X is the distance on the post from the center line. So what does that look like over here? Well, I'll show L again. That's your distance to where the listener is. Here's the distance between your sound sources. And X, and negative X, is how far you are away from that center line. Right? In that direction and in that direction. And what else do we have to describe? Well, it depends on the wavelength of your sound. So that's in the equation also. And you have plus or minus, because your plus values of m, plus 1, plus 2, give you your positions in that direction, and minus 1, minus 2 in that direction. And m equals 0 is your spot right on the center line here, and that's a maximum. And this summarizes what we said on the previous slide. The negative values of x show the location of the fringes. Fringe is another word for loud spot or no sound, below the center line. Positive values of m are above the center line. The central maximum, m equals 0, is on the center line where x is equal to 0. Right? Because if you put m equal to 0 here, you get x equal to 0. Your first spot with no sound would be x is equal to 0 plus a half lambda L over d, or 1/2 lambda L over d, and that gives you your first no sound spot. And the greater you have m, the greater order you have of the fringe, the farther away from the center line you move. Example 1. Two speakers separated by a distance of 0.75 meters are placed 12 meters from a listener. The speakers generate a sound with a wavelength of 0.20 meter. What is the distance between the central maximum and the first place where the listener detects maximum sound? We need to assign variables to our givens. So if they're separated by a distance of 0.75 meters, that's what little d is. 12 meters from the listener, That's what L is. And then here's your wavelength, 0.20 meters. And they want the first place where you detect maximum sound from the central maximum, right? The central maximum is along that center line. That's not terribly interesting. But the first place, M will equal 1. Here's the constructive interference equation. Substitute in the givens, and you get X is 3.2 meters. You're 3.2 meters away from the center line. So if your speakers are here, here's your center line. The first maximum is up here at 3.2 meters. Two speakers separated by a distance of 0.75 meters are placed at a distance 12 meters from a listener. The speakers generate a sound with a wavelength of 0.20 meters. What is the distance between the central maximum and the first place where the listener detects no sound? Once again, we translate the words into our variables. Here's the distance between the speakers, that's D. Here's the distance from the listener, that's L. Here's our wavelength. And here's the key. They want the first place where the listener detects no sound. This time you do M is equal to 0. The first place where you hear a sound away from the central maximum, you use M equals 1. But this time we use M equals 0 because we're looking for the first minima. Or destructive interference, here's our equation. We substitute in for M, 0, calculate it, and we get 1.6 meter from the center line. Waves can also interfere in time, causing a phenomenon called beats. Beats are the slow envelope around two waves that are relatively close in frequency. We'll show you what that means on the next slide. But in general, the beat frequency is the difference in frequency of the two waves. So at the top here, we have two waves with different frequencies. One's a light blue and one's kind of maybe a grayish blue. When you superimpose them on each other and add them together, you get a pattern like this, the second slide here. Look at what happens here. We've got the curve coming up a little bit, then coming down like a little peak. Where do you see that? Also see it over here. And then the pattern starts repeating itself. So from here to here is one period for this new wave. Okay? So we're going to say the beat period is 0.04 seconds, right? You go from 0.01 to 0.05 before it starts repeating itself, so that's a period. And the frequency is 1 over the period, so that would be 25 hertz. So let's go to the next slide now and see the envelope. We're putting some numbers in now. The two colors up here, blue and green, I thought it actually looks a little more gray. Oh well. They're two waves with frequencies of 300 hertz and 275 hertz. The second graph shows the sum of these two waves. The third graph shows the 25 hertz beat frequency in purple that can be heard. You could envision the envelope starting here, right? That's where we said the period started and it ended here. The envelope goes like this, and the waves are contained within it, which is pretty cool. So that period is going to be 0.04 seconds, and then the frequency is 25 hertz. And what do you notice about 25 compared to these two? Well, it's the difference between them. But what is this beat frequency? You can see that the waves oscillate, right? They get very loud, then they get soft, then they get loud again. What does that sound like? Well, it sounds like wah-wah. Now, that perhaps is not a great description of it, but click on the below picture from St. Mary's University to hear it. You've got different frequencies coming out of these tuning forks that are very close to each other. And the interference pattern, you'll hear it, hopefully you'll hear it, and it sounds like wah-wah. Example 1, beat frequency. Two speakers emit sound waves of different frequencies. The first is 525 hertz, the second is 650 hertz. What beat frequency is heard? The two frequencies are listed here, and the beat frequency is the difference between the two frequencies. So we'll write a little equation. F beat is the absolute value of F2 minus F1. Substitute in the givens, 650 minus 525, and we get a beat frequency of 125 hertz. And we just put the absolute values there in case you subtracted 650 from 525. Your frequencies always have to be a positive number.